Okay, so hi. Let's see, drop that down. Then, all right, so there's quite a bit to kind of go through in this chapter. But it's, well, it shouldn't be too bad. So anyway, last time I went through up to it's 18. Lock that thing. Yeah. So let's see. So we went through the calculation of the temperature dependence of the reaction, the equilibrium constant for reactions. So this is for gas phase, and so it's talked a little bit about reaction rate, and then it's actually calculating the equilibrium constant then, and then from that you get the reaction coordinate, right? So you know how far the reaction went, then you get the mole fractions of the product. So that differs from chapter 3, where it was just you were given the reaction coordinate. What else? That relates back to the concentration or the activity. Right? We went through that last time, and then it ties into the Gibbs free energy. So the log of the RT times the log of the equilibrium constant gives you the Gibbs free energy for the reaction, or it's a Gibbs free energy change at whatever temperature that the reaction's occurring at. You should have had that, I think, at some point in chemistry, right? The reaction constant and the Gibbs free energy relationship should be in chemistry, like organic or something, or else even before that. We went through these examples, so we should be up to 18, slide 18. Went through those examples. And then we went to this business of the temperature dependence of the reaction constant, having to do with the what we did in chapter 3, which was this delta H for a reaction, and you end up with this J constant. You solve the J constant from the 298, then the heats of formation of your components, and then the A, B, C, D for the heat capacity. Then you can get this, so you can solve for J, and then to get G, it's just do the same things, except you use that delta H to get G. So G is going to use that delta H, and then this the Gibbs-Helmholtz relationship, this delta H over T squared gives you the delta G, and then the base delta G for the 298, that ends up generating this equation, which we got last time, which has a J and an I. Right, so this calculation is pretty tedious. So there's just a KCalc spreadsheet in here in Excel. KCalc just does those. So it has J and I. J and I are down here, and then it's got the temperature, reaction temperature, 298. So you can change that to the temperature that you want, and then it goes through that calculation, right? Like you wanted it 400, and then it generates Ka 2522 from this log of Ka, which is the Gibbs. That's basically the Gibbs sum. Right, so log of Ka is going to be the Gibbs divided by RT. Should put those equations in here. So log of Ka is minus the Gibbs over RT, which is going to be like this equation, right? And J and I, if you solve by plugging in 298 into like this equation, you can get delta H from the 298 enthalpies of formation or your components, and then you plug in 298 into the T and you get J. Same way you plug in 298 for the T and get the I for the H, using the H's from formation. Right, so this kcalc has all the, you put in all the heats of formation here. So heat of formation, should make this larger. So you plug in all the blue things. You plug in the heat of formation. You get those from the back of the book, from the table at the back of the book. I'm trying to see the book here. Here it is. So the table E1 at the back of the book is all the heats of formation. And you can get them also from the, so you have like E has heats of form, oops, sorry. So E has heats of formation and Gibbs, and then the Gibbs energy formation, and it's got the A, B, C, D constants for the heat capacity equation. So you just need to look up your guy here and then plug in the numbers. So you can expand this list to any reactants you want, right? And then the reaction itself gives you the stoichiometric numbers. So the products are negative, the reactants are negative, and the products, this is making methanol from carbon monoxide. So you have two hydrogens to get the methanol, one carbon monoxide, and it produces one methanol. So that's the stoichiometric number. These numbers you get from the table, you plug in the temperature, and then it gives Ka. There's no, I think there's no minimization, right? 298. It just, let's see, is this supposed to be minimized? There's no, I think this doesn't do minimization. It just, yeah, there's no minimization, just calculates it. So why didn't Ka change here? Let's see. 10. Just calculates the J's from the 298. These are just using 298. So it's got 298 plugged in for everything. So those are fixed numbers. And then the heat from 298 comes from these 298 numbers. Then you're just calculating kind of the heat capacity changes. So this should just calculate Ka from this thing, which involves the temperature, which is what you put in, and the delta A's, which come from the A values here. Let's see, that should have changed. When did it change? Did it change? It seemed to be changing. If I did 298, that should match this number, 10.13. This guy definitely depends on 298. I'm not sure why it's not changing. It should change when I change the temperature here. Oh, I know why. It's probably, oh, there it changed. All right. It did change that time. So I think I didn't hit enter or something. This might be locked, like the how do you do that again? There's a way like this, the spreadsheets can get locked up here. It did change, but it didn't change every time. Calculation options. It's under formulas. It's on, it should be automatic, not manual. So there, it changed, right? So you have to, if it gets stuck like that, at least my Excel, sometimes if you go under formulas, then over to the right, there's a thing called calculation options. That should be on automatic, right? It shouldn't be on manual. Manual, you have to do something to make it change. So anyway, automatic, it should just change on its own. So it gives that gives approximately the same answer, right, as a 298 Ka. And then if you want it for 400, it'll give the 400. So let's do an automatic calculation now before it was somehow set to manual. It gets something I did made it go to manual, I think, possibly. So best thing is don't mess with it. But if it's not running, like it's not doing the calculations, you have to go under formulas and then under calculation options and then make sure it's on automatic. Anyway, so that's tripped down some rabbit hole here, but basically that does this calculation that's done in this example 7.4, which is done by hand here, but that just does all this calculation. Calculates first it calculates the J it calculates the I for the H, and then it calculates the J for the G. And then once you have I and J, then you can just you just plug it into this equation. It just gives the answer. For delta G, you take that's going to be log of K, so you have to take exponential of negative that to get the Ka as a function of temperature. If you don't want to go through all that, you can say that the heat capacity is constant. So if you say in that parent equation, if you say the heat capacity is constant, then the delta A terms kind of drop out, and then this becomes a much simpler expression. So you can go back to the Van Hoff equation, the Gibbs Helmholtz equation, and then just say, so you take the Gibbs Helmholtz equation, this guy, you just say delta H is going to be constant. So you can pull it out of this, and then you have just T over T squared, and the integral of T over T squared is the integral of D ln D 1 over T. Then you have 1 over G for the other part of the integral here. So you end up with ln of Ka for the other part. So you have ln of Ka versus, so this D ln of Ka versus D 1 over T. So then that just becomes this shortcut equation, this guy. So you have this is D 1 over T, so the T difference, this is ln of the K, there's a difference of the ln, so it's Ka over K reference, which is 298. That's assuming that the heat capacity doesn't change. You don't need the A, B, C, D. And then that will just give a plot of log of Ka versus temperature, which is given somewhere in here, like here. So log of Ka versus 1 over temperature. That's basically that equation, the Van Hoff equation, shortcut Van Hoff equation. Then it's basically straight lines. This is for a bunch of different reactions. So the Ka temperature dependence for all these kind of standard chemical engineering reactions. Make syngas from carbon. So you take coal and you can make it a gas, like city gas from it, right? Carbon monoxide burns, hydrogen burns. So carbon monoxide with oxygen gives CO2, right? So that's a CO oxidation reaction. There's a bunch of these commonly used. So if you have H2 and you want methane, and then if you want to have methane, you can make methanol. So you can make all your organics from methane. So if you start with coal and you want to make organic chemicals, then these are the reactions you need to do. So these are kind of the cookbook for chemical engineers. Usually you start with coal, then you make everything, right? So first you make CO, you can make city gas from it. You can just use to replace natural gas. And then you can also make methane from coal, and then you can make, because you can make hydrogen here, so you can use hydrogen and CO2 to make methane. There's other ways to make methane in here. So basically, these are kind of the reactions that you would run into if you're dealing with carbon-based society, right? And you wanted to do petrochemical from coal. So these are kind of the basic reactions that you have. Also, say you want to do a solar-based economy. So the easiest thing you can do is split water by electrolysis, or you can chemically split water with just heat using these reactions. When you split water, you make oxygen and hydrogen. So what do you do with the hydrogen? Well, you want to make hydrogen into methane so you can make other organics from it, right? So these are the same reactions you'd use for a green economy too. Right? You split water, get hydrogen, take the hydrogen, use CO2, make methane. Then once you have methane, you can do a whole slew of reactions. Right, so these are the key reactions you need to do anything. These are like the cookbook of the chemical industry. So, so it's just showing that those are all follow this over limited temperature range are all going to follow this linear dependence, meaning the heat capacity change isn't that important. In other words, these are all straight lines, log activity coefficient versus 100T is a straight line. So you can make this approximation within a small temperature range. So the idea is like, if you don't want to do these huge this kcal calculation, which is huge, that accounts for the temperature dependence of the heat capacity, you can cheat. And the cheat is usually pretty good. So it's like, there's a demo of the cheat. So here's an exact calculation of the KAs at 145 and 320 for this formation of methanol or ethanol from ethane. Right, so you have ethane, you add water, you have to run it at a high temperature, and you do this in a vacuum. Let's say you do this under high pressure, right? Because you want to go 2 moles to 1 mole. So you want to drive the reaction to the right, put more pressure in, that'll drive it. Okay, so this case is being run at heat capacity for the vapor dehydration at ethylene, and then what's the pressure? I guess this is done at atmospheric pressure. It should be done at pressure here, but I don't see the pressure. And if you want a conversion, you do it at pressure. Or you could have a side reaction that consumed the product or something that produced the reactants. So it's kind of tricks to make this happen. But anyway, he gets this thing. This just gives the Ka. The Ka is small because you didn't do it at pressure. So it's 0.1. So this reaction is not favorable. If it's less than 1, Ka is less than 1, it's a not favorable reaction. Then it's really not favorable at high temperature. Right. So it gets worse and worse. So you'd have, if you wanted this reaction to happen, you'd make a reaction that made water or made ethylene, right? And then this reaction would be driven, or you pressurize it, right? So, and then the Ka under those conditions would go higher, would become a larger number. I mean, above 1, meaning the reaction would be favorable. So that's that business. There's an example going through how to use that. This is multiple. So this is when you want to drive a reaction, or you want to. So if you want to drive a reaction, so if you have a series reaction, so A plus B makes C, and then if you consume C in the next reaction, that will drive the first reaction forward, right? And also, this is also parallel reactions. You have A being consumed in both, so that if this second reaction also is consuming A, that also drives the reaction. So the second reaction is good to use to drive the first reaction because it's consuming the reactant. So it's kind of driving it. Let's see, that's bad actually. Consuming the reactant is bad, but consuming the product is good. So the consuming the product is going to drive that first reaction. It's competing, so you'd want to put in extra A to make this work. But basically, consuming the C, having a series reaction will drive the first one. So if your product is D, you want to get rid of the C. If you have plenty of A, like if A is water, then this would drive the reaction. Both of these are going to be reasonable reactions because the Ka is bigger than 1. Right, so they're forward reactions. So both of those are favorable. But if you have 2 reactions, then there's 2 reaction coordinates, right? So you just do bookkeeping and keep track of how. So if A is consumed in both, then and if you start with 2 moles of A, so you have excess A, then it's just going to be the number of moles of A is going to be the 2 that you started with minus the reaction coordinates for both because both consume it. And then B is going to only be consumed in reaction 1. The C is produced from both. or C is produced from one and consumed by the other. And then D is produced by one and E is produced by two, and it produces 2 moles. But see, you set up this mole balance for the two you can have 10 reactions, you could have 100 reactions, right? So this approach of doing multiple reactions falls apart when you have too many reactions. You're going to have like 100 reaction coordinates. And at that point, there's another way to go at this. The other way would be just calculate the Gibbs free energy of everything and then just figure out how it runs, because you want to have a minimum Gibbs free energy from the reaction. So I'll show you how to do that at the end. But basically, if you have a few reactions, or you can minimize it and you can ignore some reactions, then this is the way to kind of solve what's happening. If you end up that you're burning something, or you have a reaction that has 100 different side reactions, then you just figure out all the species that are present and then figure out what the Gibbs free energy is for everything, and you can minimize that too. So that's easier when you have a huge slew of reactions going on, like in a polymerization or something like that. So anyway, with just 2 reactions, though, you can just do this bookkeeping for it. For these things, you're going to have 2 equilibrium constants, right? So you can set up the equilibrium constants, and they're producing, each of them produces 2 moles to 2 moles, 2 moles to 2 moles. So pressures for a gas reaction, pressure is not going to be important because you don't change the number of moles here. Also, the total number of moles won't matter because the total number of moles is constant for the reaction. So you don't need to worry about Y. You can just do this in terms of N. It's shown in terms of Y, but actually you don't need to calculate Y. So the N part doesn't change for these reactions, right? 2 to 2, 2 to 2. The total number should be constant. So anyway, so this is set up the products divided by the reactants, and then you just have these reaction coefficients, right? So you want to know the range. This gets pretty complicated. Like how to figure out the range is going to be just trial and error, and you can get it wrong, right? So it's hard to kind of get the range. So anyway, you can see that these have to be 0 or positive, right? So this reaction coordinate 1 has to be bigger than 0, because it can't be less than 0, because you'd have negative D. So you can't have negative. So, and then it has to be smaller than 1 or smaller, because B can't be negative, right? And then, so that's your limits for 1. You basically have to try each one of these, make sure it works with that, right? So if this one has to be between 0 and 1, that limits this guy. So then if this is maximum 1, and then this guy, well, this guy's going to produce E, so it has to be bigger than 0. And then this guy has to be, well, you can take NC and say that this has to be positive or 0, so that the 2 has to be less than or equal to 1, reactant 1. So that's kind of what you end up with here. The NA one is complicated because you can, so A to 1 could be 0. That means if that's 0, this guy could be 2, but you already said that it has to be, you already said that that if this is 0, that guy could be 2, but basically it has to be, already has to be less than the number 1, so it'd have to be 0 in that case. If 1 is 0, 2 has to be 0. So you see the rules start to get pretty messed up. I mean, the first equation is going to get confusing. See, so this getting these rules right isn't that trivial. And there isn't a method to do it. I think you just have to just figure out how to do it as you're going along. Let's see. All right, so that's that business. So then you're going to basically just solve these 2 equations. This thing equals a reaction coordinate, reaction constant, which you got from KCalc, I guess. Here, you just put in the free energies and got those 2 somewhere. That you got the reaction constants are given here. So So you just say that equals reaction constant, and you just solve those simultaneously. So this is, you can do that in Excel. This is 7.6. So 7.6 dual reaction. You just set up the equations and just say solve it. So this is at different temperatures, and then the reaction coordinates are going to be the things that the solver is changing. So you have two things are changing, 11 and 12. So it's like those two, and then trying to set you set up one equation, C20 for the, these are your targets, right? So C20 is this guy, and that's just going to be your K equilibrium thing. Oops, I didn't want to do that. So C20, it's just going to, that's the K equilibrium constant thing. These are the two equilibrium constant things. Oh, the equilibrium constant thing, you're getting the equilibrium constant from the shortcut Van Hoff equation in this equation. And then the thing is just these are just the equilibrium constant things. The pressure is 1 bar, so the pressure drops out of this equation. In the first equation would have pressure in it, but it's 1 bar, so it drops out. And then you just set these up to get the. So the KA's is just a box in this because it's calculated according to this Van Hoff equation. And then you use solver to find the reaction coordinates, and then reaction coordinates spit out the Y's for the components that are reacting. So that's kind of how you do this thing. That's one way to do it. So if you have two reactions, it's easy. But if you have more, it's going to be more complicated. He says trial and error, but we just do it with Excel, with the solver. He just says the same thing. It's the same, doing the same thing. Do it by hand or do it with the Excel, but doing it by hand is, the problem is you make mistakes when you do it by hand. And trial and error by hand is pretty tedious. So that's already what we did. Then, so the reason to go to multiple reactions is so that you can drive the reaction. I mean, one reason. It could be that you're facing a situation with the side reactions that happen. You want to know the extent of the side reactions that don't produce a product, right? So, or you can intentionally put in a side reaction to drive the reaction. So this is one of the earlier examples, has ethylene go into butene go into butadiene. And so this guy is actually, it's already here. It's the same reaction. So butene is this thing. It's going to go to that thing, butadiene, which is what you use to make rubber. This thing polymerizes and makes that polymer, right? Which is part of SBR rubber, styrene butadiene rubber. That's also polybutadiene is a rubber itself. This is how you make tires, right? That's a tire manufacturer thing. Anyway, so you have that reaction. You want to get butadiene because you can use it to make tires, and then you can run this other reaction, which is going to consume the hydrogen from this reaction. That will drive the reaction, right? So you could, to drive this reaction, you could pull a vacuum because you're making more moles. So if you pull a vacuum, it's like pulling the product off, right? So you have 1 going to 2. If you pull a vacuum, it'll drive the reaction to the right. You could drive this reaction by putting in steam. So if you put in steam, it drives it to the right because you put more moles on the left. So it dilutes this problem that you have of going from 1 mole to 2. Then another way you could drive this reaction is eat up the hydrogen. So you put in the water shift gas reaction, it's going to make CO, carbon monoxide, from hydrogen. And then carbon monoxide can be a precursor to a lot of other chemicals, like phosgene. You can make a lot of different things with it. So basically hydrogen looks kind of useless, but these reactions turn hydrogen into something that isn't useless. The hydrogen you can burn, right?
Wait, no. Well, hold on. Ace kills middle and bottom. So then
All right,
ogre
you guys,
kills
someone's
lady.
talking, right? Actually, someone's playing poker or something. I'm getting
No,
audio.
you can just do you. Lady's not on proc. Yeah, middle down, and then that'll. But it's if he doesn't ruin the proc rotation, he probably loses, right? I mean, you could. Yeah, actually, yeah, do that. Listen to Darway.
Oh, looks like they're muted. It's not muted. Here, AJ. Hey, AJ, can you mute? There, AJ's muted now. All right, gotcha. All right, so what do we got? So this is just showing how to do that. So it's the same thing as before. You just set up the your feed composition, and then these reaction coordinates, and then it's this CO is being fed in at 10, just like the steam was earlier. In the earlier example, it was feeding in steam, but this time this is consuming the hydrogen also. And then because of that, it's going to drive the reaction more. So you have the equilibrium constants, and then basically it drives the reaction more. That's all. I mean, you solve this, you do solver and solve the reaction equilibrium constant equations for the two reaction coordinates, and you find out that it drives it to 94.9, so 94.9% conversion versus before it was 44%. So it's 44 without steam, it was 78 with steam, and it's almost 100% conversion if you do this reaction. So you can drive the reaction with another reaction. That's the idea. So that's a case of induction, like you're pulling the product out. You're pulling out a byproduct, like consuming the byproduct and driving the reaction. So that's called induction. You can also pump, would be like creating, if you were going to create more more ethylene. So you could have a reaction that created ethylene from hydrogen that would pump the reaction. And you can do both, right? So there's various ways you can manipulate reactions. So when you get to studying reaction engineering, you're going to have situations where the equilibrium doesn't matter because the reaction's like totally 100% conversion. And in that case, it's a transport limited reaction, like how fast you can get the reactants. The reaction site is what decides the rate of reaction. And the thermodynamics of it is so overwhelming that it just happens, right? Like burning fuel, that doesn't really depend on the equilibrium constant. So you have a huge change in free energy. The reaction constant is something in the thousands or hundreds of thousands. So it's not an equilibrium reaction. It depends on how fast you can get fuel and oxygen together. So that's a diffusion limited reaction. It's not going to have anything to do with thermodynamics really, except the heat that you get out of it. It's going to be thermodynamics. I mean, the kind of reaction that we're dealing with mostly is just that it's limited by the reaction, which we aren't considering transport, right? So there's these kind of two things that feed off each other. That depends on the setup of the reactor and things. We could have so this is for continuous reactors. You're gonna have something flowing in, something flowing out. It can be in a big tank with paddles. There can be a more complicated tank where you have certain kinds of convection going on, or it can be a tubular reactor. Right, so that can be a big chemical process like this, right? And these tubular reactors are going to have various designs. You'll study these later on in the reaction engineering class. basically, this is the kind of thing we're talking about, is a reaction limited reactions in situations like this. You can also have transport limited reactions, right? So we're kind of interested in the reaction limited because that's going to be the equilibrium things we're talking about. So if you so basically it's kind of an algorithm to do these continuous reactions, right? So they do the energy balance, which is this equation. So you're going to have like the heat of reaction times, so that's per mole, right? That's an intrinsic heat of reaction. You have to multiply by the mole rate. And then you're going to have a heat change from this thing's calculated at 298. So you're going to run your reaction at some other temperature. It says an inlet temperature and an out temperature. So you have to take your reactants through heat capacity to get to the in temperature, then to the out temperature, right? And then the heat of conversion at 298. So this is kind of a balance for the energy that's going on. So you can figure out what the enthalpy is. And then you got, so you want to, if you're doing an adiabatic reactor, then you want to figure out the temperature. Like you're saying, there's no heat loss. You want to know what's this outlet temperature. But this energy balance is going to depend on the outlet temperature. So you need to iterate this thing to get this to work, right? And iterating it means you need to know the reaction coordinate. The reaction coordinate means you need the equilibrium constant. The equilibrium constant depends on the temperature. So everything depends on everything else. So in order to get this balanced out so that you have adiabatic, no heat loss in the system, you basically need to iterate this whole thing, right? You'd have to do this summation with a variation of T out, and that's going to change the K calc. I mean, the equilibrium constant, and the equilibrium constant is going to change this reaction coordinate. Then you have to feed it back to balance this out again. Right, so everything's looping here. So this is the loop that you do to do that. So first you do the energy balance, calculate the enthalpy of the inlet components at Tn, and then guess the outlet temperature, get the enthalpy of the outlet, subtract the two, then determine from that to get this to be zero, you get this rate constant at T out. I mean the reaction coordinate at T out, and then you're going to do the energy. Then from that temperature out, you also get K calc, so you can get this reaction coordinate. And then you kind of loop this thing. So this is the steps that you do. So this is worked out in this in this Excel sheet for the reactions. This whole thing's kind of worked out in this what's this called, reactions XLS. So this is let's see. (17.9) does this thing. So it's adiabatic reaction 80 719. That's the steps, and this is kind of the spreadsheet that does this thing. So you have the things you put in are the feed temperature, and then very depending on what the outlet temperature is, then you can get the you put in the feed temperature and the pressure, and you set it up for your reaction. Like this is ammonia. This is ammonia formation, right? So you're taking nitrogen and hydrogen and making ammonia. So it's 0.5, 1.5, then 1 for the stoichiometry. Should be here somewhere. Here, 1.5, 0.50. 0 is because the ammonia, there's no ammonia at the start. Those are the number of moles at the start. So it starts with a stoichiometric mixture. And then the news, I don't see the news here, but the news are just put into the equations. So this thing's going to do a loop. So it's got a solver routine for this box, which is the energy balance, to try to set it to 0. So you want to get that to go to 0 by changing the outlet temperature, D3. So D3 is this outlet temperature. Right, so it's going to just change that outlet temperature until it gets the adiabatic condition that this thing goes to 0. And then in between, while it's doing that, it's getting a new K-calc using the Van Hoff equation, the Gibbs-Helmholtz simplified with a constant heat capacity. Oh, wait, no, that's in the example problem, they use that equation, but in this thing, it's using the full Gibbs-Helmholtz equation, this guy, because it's got J and I in here somewhere. J and I are down here. So it calculates J and I each time. So it does this entire thing based on the 298 enthalpy of reaction for this reaction. So it's pretty involved. Like this whole thing is pretty involved. Basically, I guess you just need to use this thing to get the, to figure out if you have a flow through reaction, what's your conversion going to be if it's adiabatic, and then what's the outlet temperature going to be. Right, so it's going to, those two things are the two things you spit out. This is the extent of reaction, so you know how it reacted, and this is that's the outlet temperature, and you don't really have any other control except the feed temperature and the pressure. Right, in this case, you're going from so in this case, you're reducing the number of moles, right? You start with 2 moles, and then you end up with 1 mole. So basically, the pressure is going to have an effect here. Anyway, so that's kind of already set up for you to do. You might need to kind of explain what's going on here a little bit. It's pretty complicated. So I'll go through this tomorrow, because the quizzes basically use this, right? So I'll go through this stuff tomorrow. How to go about doing this. This is like a visualization of that same thing. So if you look at the adiabatic condition, so this equation for adiabatic, yeah, that equation. So you have, yeah, basically this has to equal 0. So you could divide this through and end up with an equation in terms of the reaction coordinate, which is on the x-axis here. Right, so that, or the temperature is on the x-axis. So the temperature is changing these integrals. The temperature, the out temperature here is changing this integral. That ends up being this thing, which ends up being a straight line on this plot. And the other thing is the Ka reaction stoichiometry relationship. It's like the expression for Ka in terms of the ratio of the products to the reactants. And then that thing is going to have this kind of sigmoidal shape. So the two, I mean, this is kind of, this doesn't really help much, actually, this plot, because it's already pretty complicated if you just look at it step by step, what's going on. The plot's supposed to simplify it, but doesn't necessarily help much. The only other thing in this chapter is looking at, like, if you have liquids. So the liquids, basically, you just use mole fraction. I mean, the mole fraction in the liquid state, so X instead of Y, and there's no pressure effect. So this thing for a liquid reaction is going to be much simpler. Like they show this polymerization where you're polymerizing lactic acid to polylactic acid, which is just a condensation reaction. So you take the polymer and it gives off water. Water condenses out. The more water, so you could remove the water here, it would drive the reaction. So you'd heat this up and the water would boil off, and that would make this polymerize. That's one way to do it. He's saying also, if you just put more concentration of the monomer, which is lactic acid, and it makes the reaction happen, which is kind of driving it from the left side. Anyway, so this is a case of like multiple reactions of the same thing. So you add more monomer, you get more polymer, and the polymer grows the more monomer you put in. So there's two reaction coordinates here, and then that's kind of what this is, just calculating for 2 different concentrations. Right, and he talks about the weight fraction and mole fraction being different. So the point of this is that they're liquid state. So here, when you do your calculations, use X. There's no pressure. The liquid state, there's no pressure effect. So it's just X's. Like use Y and P. And for vapors, use X for liquids. Right? And because it's so basically, because the total number stays the same, so you have 2 going to 2 and then 2 going to 2. So the total number of moles stays the same no matter how many of these reactions you do. Then you don't need to divide. You can just do number of moles. You don't need, so X would be number of moles over total number of moles. Total number of moles is constant. So that falls out of the equation, just have number of moles. So that makes it a little bit easier to calculate. So the point of this is just liquid state, you just use X. And then solid state, it falls out of the equation totally. So that your Ka equation with the solid state just goes to 1. So you just have the activity is 1. So it's like here. So here's Ka. This is the Ka equation. So for a gas, this would be Y composition times P. For a liquid, this is X. And for a solid, it doesn't change. It's just 1. So solid just comes out of the reaction. So you ignore it in the equilibrium. It's just 1. So you just forget about it. So the balance here is just going to be between CO, H2, and water. The carbon that comes out disappears. In terms of the reaction equilibrium, you forget about it. So it doesn't go back. The solid doesn't go back really. It's just 1. So the solid is like kind of ignored in the equilibrium balance. That's the effective end of it. So if the carbon's ignored, you have 2 moles of pressure to 1 mole of pressure. So pressurizing this thing will drive the reaction to the right because the carbon just drops out. So you just have this 1P. Makes the reaction go for better. And so anyway, this is that reaction, just showing that, just doing a calculation using that Ka to get, just compute Ka, that's it. So it's gas phase, so you have the Y's and the P. So in this case, you have 1 and then 2 over here, so you have 1P shows up. The lower one would be P and the top one would be P squared, so you end up with P. So it's a pressure dependent reaction. The higher the pressure, the bigger the Ka. That's the bottom line here. And then you put sub in Y with the reaction coordinate and the feed composition, you get this equation. So that's kind of that. This is showing that if you have a special kind of reaction, so if you have a, it calls an elementary reaction, right? So it means that the particles are just floating around and colliding, right? There's no coordination of the atoms to make the reaction happen. So it's just random collisions. And then you can assume that they're ideal gases. And if there's no ionic behavior, they don't make any complexes, there's no steric effects, and there's no special complexes made, then basically you can just say that the powers here are going to be the stoichiometry numbers. But if any of these things don't comply, which is the usual case, then you can't use the stoichiometric numbers. Right, so your reaction rate is the reaction rate constant, which is going to follow that Arrhenius behavior. Then this is the concentration in like moles per volume, right? So this isn't X like mole fraction, this is moles per volume. And then that's raised to the stoichiometric number because these things have all been complied with. Otherwise, this is some random number, that power that is raised to. That's the order of the reaction, right? So he shows this. I think this actually confuses things because it makes you think that you can just use the stoichiometric numbers in a rate equation. It's not true. Generally not true. It's only true under some special condition, right? So also because this is the moles per volume, then you're assuming the ideal gas law, then you substitute in the mole fraction, and you need to put RT That's just the ideal gas law coming through. Right, so you end up with RT here and the mole fraction. We aren't going to deal with this because this has to do with kinetics, and we aren't talking about kinetics in here. But this, I think, is just put in to give you an idea of how rate and so in this case, like the forward and reverse reaction ratio is related to Ka because of all these things, because it's a random reaction, because it's ideal gas, because there's no complex forming. So, you know, any number of things that makes it so that this thing is kind of Ka plus this RT thing having to do with the ideal gas business. If your sum of nus is 0, then this Ka is Kf over R. In other words, if you have same moles in, moles out, then these two are, this thing, that ratio is Ka. Like that's used to derive the Langmuir equation for absorption, for instance. But basically, generally, that's not the case. So it's a little misleading to stuff that's in that chapter. The other thing is this Gibbs minimization, which is the same as kind of the same as what we're doing. So if this thing equals ln of KT, ln of the reaction equilibrium constant, then it makes sense that this thing is going to minimize to get the products, right? So that's kind of done. So this calculating the Gibbs is the same operation, and if you plot it out versus reaction coordinate, you find a minimum, and that's the same number that you've solved for and use in solver. It's like this is the case where if you have so many reactions, right? In other words, if you don't have two reactions, you have a huge number of reactions. You may not even know what the reactions are. Like this isn't relying on what the reactions are. It's just you have all these components. What's their equilibrium composition going to be? Just using this equation. So you don't need to know what the reactions are. So if you have a huge number of components, which happens in something like burning something, then you have a lot of byproducts that come out. If you do mass spec gas chromatography on the products, you figure out what's there. Then you can figure out the heat of formation for those things at the temperature of the reaction using kcalc, for instance. So you'd have to have a reaction of formation for each of these. And then like for the primary things is 0 because they're elemental, like O2 and H2. But the others you'd have to find the formation reaction. If you get those delta G's, then you can plug those into this equation and just minimize this equation with the mole fractions to find out what the equilibrium constant is for the reaction. Right, so he shows that for this methanol, or the same reaction, right? And that's in a spreadsheet back here. So this is something called Gibbs minimization. There's a huge number of reactants on this. This is like all those things. These are Gibbs formation. Then to find this, you minimize it. So you the solver routine is just find the minimum in the sum of the Gibbs. Find the minimum in that number. Right. So somewhat straightforward given how complicated the thing is. So you don't even know what reaction this is. All you know is you can figure out the Gibbs for each of the components, and then you can put in that you want to minimize that number. So it says find the minimum. Then you're going to let the guy change the number of moles. So the thing is changing are all the number of moles of all the components. 6 to 14 are like this entire row. And then in order to do that, it's keeping things stoichiometrically with what you started with. So the number of oxygens has to stay the same. Number of hydrogens, those all have to stay the same. So this is a sum of like how many hydrogens are each of these components, right? It's summing up the component hydrogens, and then it's saying that those have to equal whatever was put in at the beginning. Oops, I'll get rid of this. Right, so this is another way. It's actually doing exactly the same math that you did with the equilibrium constant. It's doing the same math that you did with equilibrium constant. And it's just kind of, so only things that have oxygen in them are counted here. That's what it's doing, is summing up like the oxygens. And the other ones is summing up the other things. And they have to equal like how many, what was in the feed for the thing. How many oxygen, hydrogen, carbons in the feed. So anyway, this homework problem's doing that also. So this stuff should be kind of familiar to you, I think, a little bit, because you already took chemistry, you took organic. Like you should kind of know something about how to do chemical reactions. It's just kind of going through mostly something like a chemical plant, what you need to do for these. So tomorrow I'll do I'll go through the old quizzes, I guess. So there's 3 old quizzes that look good. So we can just go through those, like 2020, 2019, 2017. Those are all pretty good. We can go through them tomorrow. The 2020 does this Gibbs thing. So it's for this reaction of sulfuric acid to water and sulfur dioxide. And then it does it 2 ways. It does it with the reaction and does it with the Gibbs. So like this is the Gibbs, that same thing I just showed you, except for this particular reaction. So anyway, so I'll go through that tomorrow. So this basically the quiz will be similar to these quizzes. Right. So any questions on anything?
I have a quick question for you. I think on Canvas, all of the like submission dates are for next week. So I just wanted to confirm that we are like our homework and stuff is still due, or like when it's due.
Yeah, it's just, yeah, it'll be this, everything's like what it says on the, so it's due this week.
Okay, that's
Sorry,
fine.
I
Just
still
wanted
haven't
to
gone
check.
back. Yeah, I still haven't gone back and fixed that.
It's good. Thank you.
Yeah, but next week we'll do another chapter that isn't up there, like chapter 18,
Okay.
which is like this electrolyte stuff, which I think is pretty important. Like I think, I'm not sure if you've worked with like sulfuric acid and things, but it's kind of odd that this quiz is about sulfuric acid, because that's really like next week in a sense. But this is a strong acid. So basically we're talking about weak acids next week, like what happens when you have a weak acid. So anyway, all right. So, all right, so I'll see you guys tomorrow. Thanks.